I saw the numerous comments you left on my last video telling me that I didn't take inertia into account when I was measuring motor torque, and you're right, I completely ignored it. Now, does that matter? I don't know, it's an interesting question. Let's do an experiment and find out. Welcome back to Cloud 42, I'm James. In the last video, we tested a whole selection of motors to see what might be the best fit for the electronic lead screw project. And as soon as that video went live, I got a whole bunch of comments from people questioning whether the inertia, the actual energy stored in the rotating aluminum spool, would affect the readings as the spool came to a stop. Now, my intuition says no, it won't, but a lot of you apparently have a different intuition that yes, it will. Who's right? Well, obviously I think I'm right. If I thought I was wrong, I would change my mind, but I don't know. Let's do an experiment and see if we can figure it out. If you remember from last time, this is our test setup. We've got the motor mounted in the vise here with an 80mm spool. So the radius is 40mm, which is 1/25 of a meter. And then we've got a cord wrapped around it to apply tension and brake the motor to a stop. And when the motor actually comes to a stop, we can measure the force that was required to stop it with this force gauge. And then we take that, multiply it by 25, because 40mm is 1/25 of a meter, and that will tell us the torque that the motor was able to output, or more accurately, the torque that it took for us to stop the motor. So we just spin the motor up, it runs, I gradually tighten the loops, and 31.3 newtons. That's the force that was required to stop the motor. So we just take that and divide that by 25, and that will tell us the torque in Newton meters. Now, many of you wrote in the comments to talk about this aluminum spool, and the spool is not, light, it's a solid chunk of aluminum. And so there's some mass here. So when this is spinning, especially at high RPM, there's some energy stored in this. And when we pull the cord and when we bring this thing to a stop, we're stopping the motor, we're overcoming its torque, but we're also taking the energy that's stored in that spool and dissipating it into heat, in friction. The question is, does that affect the reading? Now, my intuition says no, but let's take a little bit closer look at what's actually happening here and explain why I think that. And then we'll test it and see if it's actually true. Okay, you always know you're in trouble when I get out the engineering pad. Don't worry, we'll get through this together. So this is the spool we're using, and let's kind of draw a picture here of what's actually happening. So we've got the spool here, and it's attached to the motor, and the motor is generating some kind of torque. And we want to measure how much of that torque. So we take a cord and we wrap it around. I'll just show one wrap. And that cord is producing friction against this. Now I will pull gently on the end of this cord. Now it's important that I pull this very gently because any force that I pull on this will be directly measured through the hook of the force gauge up here. So if I'm pulling here with 10 newtons, that's going to add 10 newtons to this. So the goal is get enough wraps on here that I can pull this very, very gently, a newton or less if I can, just to generate the friction force that we need to actually stop the motor. So if we draw in the radius here, at the time we stop the motor, there is a force pulling up in that direction that's on this cord. That's the actual braking force, and the motor is trying to generate a force pushing down. It's rotating against that. So once this comes up to speed, these two forces will be equal because as I start to tighten this, it'll generate this force that's trying to stop the motor, and the servo drive or the closed loop stepper drive will produce additional torque to try to counteract that. So as this force increases, the motor will increase this force to try to counteract it. So the spool will continue spinning at a constant speed. It's got inertia, but there's no acceleration happening because these two forces offset each other exactly, and so there's no net torque actually being applied, or rather, there's no net angular acceleration because these two forces are equal. At some point, what will happen is we will overcome the motor's ability to produce torque. It will detect that it's falling behind and it will shut off. Then this force that's being generated by the motor will go away. The only force here will be the force pulling up this direction through that friction, and it will slow this to a stop. And we'll see that as the motor shutting off, probably hear a clunk, and this will come to a stop. Now let's talk about what's actually happening with the friction force. If you took physics in school, you'll remember the equation for friction. So assuming that we've got something that this box is sliding in this direction, there are two forces acting on this. It's sliding along this surface and there's going to be some amount of friction. Well, how much friction will there be? Well, we can figure that out, that the friction force equals the normal force times mu, which is the coefficient of friction. So the normal force is the force of gravity in this scenario here, pushing our object against the surface, and that generates a friction force this direction that opposes the motion, and that is just dependent on the normal force and mu, the coefficient of friction. And the coefficient of friction is just a constant for this given setup, determined by what the materials are, how much contact surface there is, what kind of lubrication might be there. But you'll note that the force is only dependent on the normal force and mu. The exact speed this is moving, whether it's accelerating or decelerating, none of that matters. It's simply the normal force and the coefficient of friction. Now the same thing is happening here, except the normal force is from the cord pushing in all around the spool. And that normal force is controlled by how much tension I put on this, because if I put tension on the free end, that causes that squeezing, that normal force of the cord pushing in against the spool. And there's some coefficient of friction, mu, in this system that's determined by the materials of the cord, the material of the drum, and the characteristics of the roughness of the surface, and if I got any grease on it from my hands or how much aluminum is packed into it. But that mu is a constant, and so the normal force and mu determine this friction force here that's trying to stop the spool. Now note, there's nothing in this equation about how fast it's turning. There's nothing in the equation about how much inertia is in here. There's nothing in the equation about whether that's speeding up or slowing down. It's simply the normal force, which I control by pulling on the string, and mu, which is a constant. So what that means is it's not really the motor or the inertia in the spool or anything else in the system that's generating this force that's being measured up here. It's me pulling on the string, given that this is in motion, that's generating this force, which of course is counteracted by pulling down on the hook, and that's what's being measured by the force gauge. So based on this analysis and based on my intuition, it shouldn't matter. The inertia doesn't even enter into this, and it shouldn't matter. So what does happen? What does the inertia affect? Well, at that moment when this is spinning at a constant speed, you've got a constant amount of energy in this as it's rotating. And as it's rotating, the moment the motor stops pulling on it, now we have a net force pulling up that's trying to stop this from rotating. And the energy that's in this will cause it to continue rotating for a little while. How long? Well, it depends on what the force is. So you've got the rotational inertia here. You've got a force pulling on it. If that force is very, very gentle, then this will take longer to slow down. It doesn't suddenly increase that force because the energy is coming out from the inertia. It just will take longer to slow down. If this force is low, it will slow down faster if this force is high, and that's entirely controlled by how hard I pull on this. So it really shouldn't matter. The inertia should just cause it to spin a little bit longer after the motor gives up. Now, I also got a bunch of comments about how many turns were wrapped around this. Now, the issue is that if I just put one turn around it and use that for all the tests, when the motor's running slowly, when it has a lot of torque, or when I'm measuring a motor with a very large torque, I have to pull hard on this cord to generate enough normal force that when multiplied by mu gives me enough torque, enough friction to actually stop it because the torque is so high. And the more I pull here, all the force I pull here appears right at the force gauge. So the harder I pull, the more error there is. So what I do is I put more and more and more turns around this until a very light tug on this string will generate enough force to stop the motor. Why don't I just leave all those turns on all the time? Well, it turns out there's a minimum amount of friction, because even if I leave this completely slack and I'm not pulling on it, gravity's pulling on it, the cord around the top is sitting on it, causing it to drag and causing it to pull tight. So if it's running really fast and I have a whole bunch of turns on it, it'll just grab and stop the motor. It doesn't grab, but there will be enough friction to stop the motor before I even start pulling. So my goal in changing the number of turns is to find the point where it doesn't stop on its own, but a very light tug here does stop it, because I'm completely ignoring, I'm not measuring this force. So I'm trying to minimize that to minimize the error. So let's figure out, how would we find out if all of this is true? So if everything I just told you is correct, then the inertia of this spool doesn't affect the outcome. Well, how would we do an experiment to find out if that's true? Well, this spool weighs, let's see, I wrote it down over here on the other one, 364 grams. So it's actually a lot heavier probably than it looks. It is aluminum, but it's still 364 grams. Well, I just 3D printed another one out of PETG, and this is only 69 grams. So this is just a fraction of the mass of this one, so it should have a fraction of the rotational inertia. So in theory, if we test with the aluminum spool and then test again with the lightweight plastic spool and we get the same result or close enough, then we can say the inertia doesn't matter. Now there's another factor in play here, and that is that the coefficient of friction, mu, is going to be different for these because these are two different materials. But in theory, that also should not affect the results, because I can just change the number of wraps so that the same light tug down here gives me the same amount of actual drag, friction force slowing this down. That'll be measured on the force meter, and as long as the tension that I feel pulling on this cord is about the same, then the results we get should be about the same. Okay, I've got the same spreadsheet up we used last time. I hid the data from all of the other motors, but I've got right here the KL5080H driver. This is the 2 Newton meter setup from Automation Technologies, and that's the one we're going to use for the test. I'm not going to retest everything, I'm just going to do the one. So we have the data that we generated last time. I'm also not going to mess around with the holding torque and everything else. Since the question is just about high-speed performance, I am just going to test the data above 500 RPM. So I'll go ahead and take the old data out, and we'll start by retesting just to make sure we can replicate the results we got last time. So last time at 500 RPM, we got 31.2 newtons. Let's see what we get this time. That's 500 RPM. 31.5. Let me run that one more time because I felt like I tugged on it a little bit. Let's try it more gently. 31.1. So, yep, that was great. 31.1. And let's take it up to 1,000 RPM. $20.7. And 1,500. I may need to take a loop off. Let's see what happens. 15.6. And that compares to 15.4 last time, so you can see these torque curves are identical. Okay, now let's see what happens with the plastic. Now, I have not actually tried this. In fact, I don't even know if it's going to work. I don't know if the plastic's going to be strong enough, but we are going to find out together. Okay, now this may wobble a little bit. but let's give it a try. I'm going to start with 2 wraps here because I'm not sure how much friction this is going to take. And let's go back to 500 RPM. Okay, let's give it a try. Again, this plastic's a little stickier, so it wouldn't surprise me if this just grabs and we have to go with fewer wraps. Let's find out. Okay, there we go. $22.8. And that is not at all what I expected. Let's reset this and try this again. $23.6. That is interesting. Oh, now that's interesting, 30.6. That's much more like what I was expecting. I wonder if I've got some issues with the smoothness of the plastic here. Of course, that would just be changing the coefficient of friction, but I wonder if it's specifically the little nubs that are on here are actually grabbing the weave of the cord. Let me run a file over it, or some sandpaper here real quick, smooth it out. Yeah, there's definitely some roughness here. Now let's put this back on and try that again. 500 RPM. $26.0. $28.9. Yeah, the plastic is a little bit less consistent here. $30.4. $26.0. Okay, so let's call it, let's pick something right in the middle there around 28. And let's go ahead and bump this up to 1,000 RPM and just see what we see up there. $20.5. And that is exactly in line with the other number. And that took almost no force on here. So let's go ahead and bump that on up to the next one, which would be 1,500. Now see, this might be too many turns of the cord. This is really grippy. Yep, it's too grippy. Let me back off to just one loop. Yeah, we're definitely grabbing. Oh, that's something I hadn't thought about. It's melting. $16.3. That is just about what we got on the other one. Let's do that one more time. See if I can do this without. See, once it grabs, it's actually grabbed and cut into the plastic. And I think the plastic of the cord has melted to the plastic of the spool. So let me try it loose and we'll try it one more time. 14.1. So we've hit 16.3 and 14.1. We've hit just a little under the last number. Now that I realize what's happening, that's sticking, let's try this one more time. 14.7. And that's kind of right in the middle. We'll just take that number. Okay, now I want to go back and check out this 500 now that I understand what's happening here, that this is actually sticking. Let's try the 500 again. You're getting to watch this live because I hadn't tried this before and I haven't worked all the kinks out of the testing setup. Okay, 500 RPM. 29.9. Did not anticipate the material issue. So that's another thing that I learned using PET G with a nylon or with a nylon cord against it. It's getting some melting and some fusion and tearing up the surface. So that is something I learned, but I think we have the data that we need. So I think it's clear from looking at this that we actually don't have very much difference here. Now, I was really not expecting that plastic to be so sticky. I did not expect it to melt. I did not expect it to fuse with the nylon cord. I think if we used some other material that had a smooth surface, or if we hollowed out the aluminum spool just to reduce its mass but leave the same surface on it so that it was impervious to melting at these speeds, I think it would have been a little bit easier to get these results. Now, the results I got here ultimately look very, very similar to me when we plot these curves right next to each other. This is enough to satisfy me that my intuition, based on my analysis of the physics of the situation, is correct. Now, there is some experimental deviation there, and I think I understand one of the reasons for that is, again, just the material, and like you can see the marks that got left in this, and it's rough, and it was snagging, once it started melting, was snagging in the cord. But even with all of that trouble, we still got very, very close to the same results. So I'm satisfied that the inertia is not really an issue, that it's just slowing things down. This would have braked to a stop much more quickly because for the same force being applied, there's less rotational inertia because there's less mass, so it would stop more quickly. But other than that, it doesn't affect the testing results, at least not substantially. I would consider this in the noise. In the last video, I promised to test one more motor, and that motor is now here. This is the 180 watt integrated servo from Stepper Online. And just playing with this motor, it feels really nice. There's no cogging, so it's definitely a servo and not a stepper. And I can spin it up and it runs great. However, it's not very stiff. And I think this is because the default settings are more concerned with speed than they are with position. And to change that, I need to be able to connect a computer and change it in software. And try as I might, I have not been able to get the software to connect. I'm talking with their tech support, and once we get that sorted out so I can actually stiffen this up and put it into position mode and give it a fair shake, we will test this one as well, and that will be coming up in a future video. If you enjoyed this video, please give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. In fact, this whole video was born out of viewer comments. Thank you for watching.